So if you remember at the beginning of the year when we kind of talked about how this course was going to be set up, I had mentioned that this course was largely going to be a survey of functions. And that's really what we've been talking about in Chapter 1 here in general. It's just about like what a function is and what are some ways that we can describe a function and the properties of functions. And then out from this, we're going to look at different types of function groups. This first situation, or this first chapter after the introduction, we're going to be talking about absolute value functions. And in each of these function groups that we're going to talk about, we're going to be concerned with three primary skills. We're going to want to be able to graph that function. We're going to want to be able to simplify the function. And then we're going to want to be able to solve equations involving that function. So these are the three primary skills that we're going to see in, or be addressing in each one of these major function groups. Now there might be additional skills inside a given function group, but we will always talk about these three skills for every set of functions that we talk about in this class. So the tools that we developed in this first chapter, talking about domains and ranges, and increasing and decreasing, and maximums and minimums, and these sorts of language we're going to be using kind of throughout. And that language will apply to each of these function groups that we're talking about. The ideas of transformations and graphing a transformation, again, is going to carry through to all of these function groups that we're going to talk about. So this first chapter that we just finished was very much big picture things. And now we're going to start applying those big picture ideas to these specific instances. Okay with that plan? Okay. So I'm not going to fill in the rest of the functions here. I just wanted to give you, again, rehash kind of what the structure of this course looks like and how what we just finished talking about relates to these things moving forward, to give you a little bit of a visual on the organization for the course. Does that feel okay? Okay. So Chapter 2 is going to be about absolute value functions. And our first lesson is going to be about graphing absolute value functions as the main focus. I'm sorry, what? Yeah, we're going to talk about what the graph looks like in just a moment, but yes, kind of. I think I know what you're talking about. So before we talk about graphing an absolute value, we really need to kind of describe what this thing is and what the definition of an absolute value is. So let's start with that. So this first definition is our geometric definition. We're also going to look at an algebraic definition after that and talk about how they really mean the same thing and why you really would want two definitions for the same thing. Everybody's okay with this idea? Bless you. So our geometric definition reads absolute value written as a vertical bar, some quantity, and then another vertical bar, represents the distance between x and 0 on the number line. So if I think about this visually, let's say here's our number line. Here is 0. And say we're talking about the absolute value of -5 here. So we're talking about that distance. Everybody agree with that? So if I count that up, let's see, that's 1, 2, 3, 4, 5 units away. So I can say the absolute value of -5 is 5, because -5 is 5 units from 0 on the number line. 0? So we'll talk about that this is not a very practical definition, right? So the reason that we've defined things in several different ways is because in mathematics, absolute value might be useful inside of a geometric setting or an algebraic setting. And then we'll talk about practically, like how should I think about this in a practical sense to deal with problems. All of these different ways of thinking about these mathematical concepts are going to be important. And certainly if you hold your question, I think I'm going to describe exactly what it is that you're going to ask. But I think it's all important that we see the different ways to think about these things. Because if you're doing a story problem, the geometric interpretation might be really valuable to you as opposed to just taking the absolute value of -5. So I want to make sure we kind of approach these other ways of thinking about these quantities so that when you see something maybe unfamiliar, you have more tools or ways to think about a problem that you would otherwise. But yes, I fully acknowledge that there's a more practical way to think about this than what I've presented here. And I'm getting to the practical way here in a moment. Okay? So the takeaway here is if I'm describing the output of an absolute value as a distance, what can I say about all distances? Right? They always have to be greater than or equal to 0. If I called you up on the phone and asked you how far are you away, and you said -3 miles, I would scratch my head because that answer doesn't make any sense at all, right? Regardless of which direction you are away from me, you just say I'm 3 miles away. Intuitively, we have a sense that distance is only positive, right? You never answer like a how far are you away with a negative number there. Agreed with that? So, in a sense, the practical way of thinking about this is that the absolute value is just going to remove any negative. It's always just going to make whatever the quantity is positive. Everybody's okay with that idea? Yes. Okay. So, and I think, Sierra, that's probably what you were going to ask, right? Was that the case? It is honest. What I said was that the absolute value essentially removes the negative, makes everything positive, right? And I think it's important that you see that practical description that probably most of us are most familiar with is really the same thing as this more formal definition, right? It's still saying the same thing. And it's important that we understand that the definition is kind of saying the same thing. There's another definition for an absolute value. This is our algebraic one. So this one we're going to define just symbolically. So I'm going to have the absolute value of x equals, and then I'm going to draw a large version of this squiggly bracket. What I'm going to write here is something that's called a piecewise function. I'll describe in a moment why we call it a piecewise function, but just you'll probably see why in just a moment. So the algebraic definition for an absolute value says the absolute value of x is equal to x if your input was greater than or equal to 0. Otherwise, the absolute value of x is equal to negative x. That is, when x is negative, I negate it. So let's see an example of kind of how I use this definition. So if I'm taking the absolute value of 5, in this case, x is equal to 5, right? So since 5 is greater than 0, I know then the absolute value of x is just x. Or the absolute value of 5 is just 5. So the absolute value of positive will give me a positive number back, right? If I have the absolute value of negative 5, here our x is negative, so I'm going to use this piece of my piecewise function. So that's going to tell me the absolute value of negative 5 is equal to the negative of negative 5, which makes a positive. So again, this definition is describing what we intuitively and informally understood the absolute value to do, which was just it gets rid of negative signs. Because anything that was negative, we negate to make it positive. Anything that was positive, we don't change at all. Everybody okay with that idea? Okay. So before we get on to the graphing part, I want to talk a little bit about simplifying. Because it's important that we're able to manipulate an absolute value, a statement with an absolute value in it if we're going to be able to graph it. So we're just going to look at some rules here. And I'm just going to number these kind of 1 through 5, or 1 through whatever. I can't even remember how many I'm going to have. And I'm going to start with the statement. We're going to decide whether this is true or false. Okay? What do we think? Is this true or false? So it seems like we're split. I've heard lots of people say true and lots of people say false. Let's test it out. So let's pick a value for x. 2. And let's pick a value for y. Let's pick a negative number, though, because absolute values definitely affect negatives and positives differently. And let's see if this gives us the same thing. So if I have 2 plus negative 7, take the absolute value, and I take the absolute value of 2, and then the absolute value of negative 7, let's see if these give us the same thing. They do not, right? So this is false. This is not true in general. Could it be true in a specific instance? If everything was positive, it would be fine. In general, though, this is never okay to do. So this is false. Do not do this. What are we basically saying that you cannot do? You can't break an absolute value up at an addition symbol. Could you do this breaking the absolute value at a subtraction symbol? No, it's the same thing, right? Everybody's okay with this. This is the most common mistake students make with absolute values, is that they break them at an addition or subtraction symbol. Clayton. Absolutely. And you might be thinking, okay, you said that's the most common mistake students make. How are students making that mistake? Well, let's look at this possibility. Let's say we have the absolute value of x times y And then we'll see if that's equal to the absolute value of x times the absolute value of y. What do we think about this one? Is this true or false?
True.
Okay, you guys think it's true. Let's test it out just to be sure, right? Let's use the same x and y that we did before. And let's see what we get. So that does look like it's right. This is true. So this is why the previous is the most common mistake. Because we can break up an absolute value over a multiplication symbol. Do you suppose we can do this with division also?
Yeah.
We can. So you can break an absolute value at multiplication or division. You cannot break that absolute value at an addition or subtraction. Everybody's okay with that idea? Okay. What about this? Is this true? The absolute value of x minus y equals x plus y.
No.
Definitely not, right? What does it look like we did? We just took the absolute value of the pieces individually, right? This is really the same thing as number 1. Can't do that. I see frequently students do this. Historical evidence says that this is a frequent mistake. Please do not do that. That is false. You cannot do this. Okay. So those are some simplifying rules. That's enough for us today to be able to do the graphing parts. Okay? We'll continue to kind of tack on some more simplifying rules as we need them. But for today, if the main focus is on graphing, we've done enough to do our graphing. So we're going to think of the absolute values as a transformation of the parent function and in this case, the parent function for absolute value functions is just y equals the absolute value of x. So if I look at the graph of the absolute value of x, it looks like this V shape. There are 3 key points that we're going to be interested in. It's the point 0, 0, the point 1, 1, and the point negative 1, 1. Yep, short for parent function. So one of these points has a special name. Well, 0, 0 is referred to as the vertex of an absolute value. It's the point of the absolute value. It's like the place where the 2 lines meet. So in a way, Michael, what you're describing was correct, and the graph of the absolute value is made up of like 2 lines, basically, or 2 rays, more accurately, since they only go in one direction. Everybody okay with that? Okay. So let's say then we wanted to graph y equals -2 times, actually let's not do it one of those yet. Let's just do absolute value of x plus 3 minus 1. What I'd first want to do is identify my a, h, and k. So I remember that in general, functions were a times f of x minus h plus k. That's for the parent function y equals f of x. In our specific case, our parent function is y equals the absolute value of x. So what this is going to change into is going to be a times absolute value of x minus h plus k. Because our situation, f of x is the absolute value of x. So you're correct in saying that the a value is 1 in this case, right? Because there's no coefficient out front. H is almost 3, -3. Remember that the sign of the h is always opposite of what it appears. Most common mistake students make in graphing is screwing up the sign of their h. And the k is -1. The k's are the same sign as they appear. So what I'm going to do then is I'm going to use my transformation map. So you remember that this is x plus h, ay plus k. And I'm going to use my 3 key points. So if you recall from the last chapter, this was our transformation map that we can use every time to view some function as a transformation of its parent function. I'm using this same concept now to do my graphing specifically for absolute value functions. Is that okay? So this is something that you'd probably want to memorize. We're going to use it a ton throughout the entire course. It'll be a good one to have memorized. So if I plug in -1 for x, and we said that our h in this case was -3, our a was 1, plug in 1 for y, and then -1 for k, and I get -4, 0. And then I get -3, -1. And I get -2, 0. Everybody okay with how I calculated those 3 points? So to graph this absolute value function, then I'm just going to plot these 3 points. So I'm going to plot -4, 0, -3, -1, and then -2, 0. And I'm going to get this. Everybody okay there? What is the vertex in this case? What's the coordinates for the vertex for this graph? -3, -1. Remember, the vertex is right here. So in our parent function, the vertex is at 0, 0. In our transformed function, the vertex is at -3, -1. Do those numbers, -3 and -1, hold any significance? So what we can say then is the vertex therefore, any absolute value function in the form a times x minus h plus k is the point h comma k. I can determine the vertex by just looking at the shape of the equation. I don't need to look at the graph. I can do it just from the equation. That's pretty nice, right? So that's a nice little fact. Let's do another graph. So let's say we want to graph y equals -2 times the absolute value of x minus 3 minus 4. So I would start by noting the values for a, h, and k. My value for a is?
-2.
And my value for h is? Good. And k? -4. Very good. So using this, I can write my transformation map. What is my transformation map going to be?
X plus a, comma, ay plus k.
Everybody okay with that? And then, just like before, I'm going to take the same 3 key points. Every time I graph an absolute value function, I'm going to use these same 3 key points to generate my graph. So I get 2, -6, and then I get 3, -4, and then I get 4, -6. I omitted plugging in the x and y into the transformation map, but after showing you guys how to do that once, I assume that's not a big deal. Right? I just did a little bit of mental math there. So if I graph this, what do I get here? Let's see, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So I have 2, -6. Didn't get colored. 2, -6. Try again. 2 is right there. 3, -4. And then 4, -6. Everybody okay there? So again, generating these graphs, pretty easy once we have these transformational tools that were kind of hard to come up with, right? When we did that, it seemed a little bit weird when we generated those formulas. But you can see now, as we start using those formulas to do things, that it's actually a really effective technique. Okay. How do we feel about this? So far, so good? Good. All right. So let's look at some observations. One is that we said the vertex is h comma k. We said that already. 2, let's look at the domain. Remember, the domain is about which coordinate, x or y? X. So if I look for a leftmost point, there is not one because it goes on that left arrow, so I have -infinity. And there's no rightmost point. I have an arrow to the right going on, so I have +infinity. All absolute value functions' domain is -infinity to +infinity. The range is about which coordinate, x or y? Y. So notice we have two separate situations. When my graph looks like a wedge, my arrows point down. There's no lowest point. But in the previous example, when my graph looks like a V, my arrows point up, there's no highest point. So we're going to have two separate situations depending on whether the graph looks like a V or if it looks like a wedge. So if the graph looks like a V, then our range is going to go, the lowest point is the y-coordinate of the vertex, which is k, up to positive infinity. And the k is included because that's the y-coordinate of the vertex is a point with that y-coordinate. And if the graph is a wedge, then our range is going to go from negative infinity up to k. Can I tell from looking at the equation whether the graph is going to be a wedge or a V? Yeah, it's going to depend on the sign for A, because remember, A controls whether there's a reflection across the x-axis. So if A is positive, we have no reflection, so it's going to look just like the parent function, which opened up. If A is negative, there will be a reflection across the x-axis, and it'll look like a wedge. So I can tell just by looking at the parent or at the equation what the domain and range is going to be. I don't even need to look at the graph. That's pretty cool. How about increasing? Again, there's going to be one increasing part and one decreasing part, always for absolute value functions. But there's going to be two cases. If the graph looks like a V, the second half of the graph is increasing. So that starts at the x-coordinate of the vertex, which is h, to positive infinity. And if the graph is a wedge, it starts increasing, so it starts at negative infinity and goes to the x-coordinate of the vertex. Yes, sir. Of course. Similarly, for decreasing, so if it's a V, then we start at negative infinity and go to the y-coordinate of or the x-coordinate of the vertex. And if it's a wedge, we start at the vertex, x-coordinate of the vertex, and go to positive infinity. So again, I can write increasing and decreasing just by looking at the equation. I don't actually need to look at the graph. For the extrema, an absolute value function is going to have exactly one extrema. It's always going to be a global. If we have a V, then the vertex is a global minimum. And if it's a wedge, then the vertex is a global maximum. So let's say we want to analyze this graph, y equals negative absolute value of x plus 1 minus 2. So, what's my vertex? Actually, let's start by listing the a, h, and k. That's probably the better place to start. My a is negative 1. My h is negative 1, and my k is negative 2. Okay. So my vertex is always h comma k, So it's negative 1, negative 2. My domain is always negative infinity to positive infinity. My range depends on whether I have a V or a wedge. Since my A is negative, I have a wedge. In the case of a wedge, my range starts at negative infinity and goes up to K. Notice us doing this all without actually looking at the graph. This is nice, right? Increasing. So I know if my graph looks like a wedge, my graph begins increasing and increases all the way to the x-coordinate of the vertex. And then it decreases from the x-coordinate of the vertex to positive infinity. And because it's a wedge, I know I have a global maximum at that h comma k. Everybody okay with that? If I wanted to describe this transformation in words, I'd write my 1, 2, 3, 4. Since my A is negative, I have a reflection across the x-axis. Since the absolute value of A is 1, I have no stretch or shrink. Since my h is negative, I'm going to go left, and because it's negative 1, it's 1 unit. And since my k is negative, I'm going to go down, and since it's negative 2, it would be down 2 units. So we've just added a bunch of rules here, but what can we always default to if we don't like any of these rules? We can just look at the graph, right? You can always look at the graph and determine these the same way we did in Chapter 1, but the goal here was, rather than having to look at the graph every time, we've been able to discern that we can just look at the equation and use the values of A, H, and K, and not actually have to do any graphing to figure these things out. Okay with that? That's going to close section 2.1 for us. So what I'd like you to do is to do 1 through 11 odds, and then I'd like you to do 12 and 13, and then 15 and 18.